All right, here we go. So, pointers. People get scared of pointers at the time. In fact, like, people dread pointers. Like, it's got a stigma associated to it. But my job today is to show you pointers in the most easy and clean way, so that we don't, you do them right the first time, and you avoid as much as possible crashing. It's gonna happen. You want to use the debugger for that, definitely. But at least, you get the good fundamentals done. So, what are pointers? Let's just start out with the most basic idea of what is a pointer, okay? So, when you're creating an object in C++, right now, you say something like int a, okay? Internally, in the computer, behind the scenes, per se. Behind the scenes, your computer is, if you think about von Neumann's diagram, you have your CPU, and that CPU is in the motherboard, and that motherboard is connected to your RAM. You got probably some RGB or something going on, okay? On the other hand, your motherboard is also connected via the SATA ports to some sort of external storage. It could be a hard drive, or it could be, if you have a newer PC, an SSD, or even an M2 drive. These are all storage types. Obviously, M2 is fastest, but hard drive and SSD are pretty good, right? I even know that I've heard today, that I didn't know the thing, that they have RGB SSD. I was like, oh, okay, interesting. There's, of course, other things, like you might have a PCI Express port connected to a 3090 or something, if you were lucky with the shortage. But I guess if it's a 3090, it would be like 10 times bigger than that. But yeah, the point is that when your computer, when you're working with your computer and you're creating a variable, let's kind of focus right now on this, which is the memory, and how it communicates to the CPU. Internally, there has to be a way of organizing the memory, right? The game chart, yeah. The memory is organized by addresses. Think of like a really, really, really massive array, like a massive, massive array, okay? From 0 all the way to like 4 billion, okay? That's basically how RAM works. They all get addressed into these little pieces. Now, I'm not going to go too in-depth into that, so I am going to cut a lot of corners. But 219 is going to be all about this stuff. You'll spend some time learning about addressing, different addressing methods, and then 370 will enhance that knowledge. So you're going to see this in detail in future classes. Right now, the main job here is programming. But so you can understand that you have to know a little of the basics, right? For now, I'm going to say that the way the addressing works is not in decimal, first of all. That you might have guessed. It's actually going to be in hexadecimal. It's in binary, but it's sort of abbreviated in hexadecimal because it just works out better that way. Hexadecimal means base 16. That means you go from 0 all the way to 9, but then you don't put 10. You keep going, and we just chose to use letters because we're not that creative to come up with new symbols. So we said hexadecimal is going to have the letters A, B, C, D, E, and F associated with it, which would be like a 10, 11, 12, 13, 14, and 15. So then 0 to 15 is 16 digits. And that's basically how you address your system. So you start out with address, and the way you see hex, you usually see a 0 and an X in front of it. That means that the number after it, so if you see a 10, that's not a 10. That's a hexadecimal 10. Hexadecimal 10 is actually going to be 16 because you go from 0 to 9, and then technically you have an F, and then from F, you go to 10. So you could also have like 1A. And once you get to 1F, the next thing you get is 20. So when you see this here, it's not a 10, and it's not a binary 3, which would be 10. It's actually going to be a, wait, I said 3, sorry, 2. It's not going to be any of those. It's going to be hex, okay? And so because of the size of the space each variable takes, it turns out that an integer takes 4 bytes, and a double takes, I believe, 8 bytes. A float, I think, takes 4 bytes, and so on, okay? But really, the only ones you should kind of know for now are going to be int and double, okay? A car, I guess, technically speaking, a car only requires 1 byte, I believe. Yeah, 1 byte. So 1 byte for a car. However, most modern computers just actually use 4 bytes. So unless you have the cars next to each other, they might take 4 bytes. Okay, so just keep that in mind that this one's kind of iffy. Okay, but these are definitely true for that most of the time. Like depending, I mean, it's going to depend on the system. Like back old school days, you know, it could be actually less, but modern computers are going to be that. So again, the reason I'm telling you all this is because of the way that memory is structured. So when we have an address, and I say to you, okay, there's an address in your computer that is address 200, whatever that means in hex. In fact, if you want to convert hex to decimal, just Google hexadecimal and like put like 200 hex to decimal, and you know, if I share my screen here, I literally just went and Googled. So here's Google hex to decimal. You know, I have a bunch of converters, but actually I can just type in Google 200 hexadecimal, and I get that that is actually the value of 512. Now that's not a, you know, coincidence. It's because of the binary, how that works. Okay, so that's a nice conversion. If you ever need to convert that, of course you could code it yourself too. In fact, I might have some code like that in Canvas. But the point is that the next spot here is going to be address 204. Well, I say 204, but again, that's not 204 in decimal. Okay, so it's 204. That's because the difference from 0 to 4, that's 4 bytes, because that's how long an integer takes. Now, if we had an address here, 300, and this was a double, then the next available spot would be 3008. Now, let's say that, you know, beneath that, I have, so here's the double. Now I have an int, so let's say I want to put an int in here. The next address is going to be 30B, right? Or B or C? Hold on. It'll be 9AB. 1, 2, 3, 4. 9AB. C. Not B. I have to do 4. So like 8 plus 4 in hex is going 8, 9, A, B, and C, right? Which would be like 9, 10, 11, 12. So yeah, 12. Okay? So that's what gets you sometimes. You got to remember that how to do this math, okay? So that's how memory is stored. You get this hexadecimal address, and then that is that's literally where your variable is stored. So when I say in my computer, int A, behind the scenes, behind the magic, somewhere in my main memory, the computer picks a spot that is 4 bytes long, gives you back an address, and says, well, probably not 11110, and says, congratulations, this is where you're going to store your A. And then when you store your number, let's say you're storing the number 42 in there, internally the computer is dealing with these addresses. But you don't want to deal with those addresses because it's just too much effort. You deal with nicely named variables called A. Well, you probably want to pick a better name, May, but the point is that you're not dealing with some numbers, right? When you compile this code, if you have taken 218, which I assume none of you have, because that's, I think, after 202, but I guess in theory you could. I don't know. Oh no, it used to be you could, but then we changed the rules to make it so you have to take 202, because really, like, you really should take 202 before 218. It gets really hardcore in 218. 218 is assembly. When you compile your code, it becomes assembly code. In assembly, you might actually see the addresses there, but not even then, because here's the catch. These addresses, this time around we got this address 110. Next time I run the program, I may get address 300. There's nothing defined that says like you have to get this address. That is completely up to the operating system. That's the person that handles it. It's like, think about going to a hotel. You check into the hotel and the lobby, and they give you a room. You know, they give you the key to the room, and then say, and you say, I would like a room with 1 bed or 2 beds for 3 days. So you go in there and they assign to you a room based on your specifications, that you want space for 4 people or 3 people and that you want it for this amount of time. When it comes to a computer, you don't particularly have to give it an amount of time, but you have to say how much you need. So it's the same thing. The computer goes to the lobby, which is the operating system, and says, hey, I would like to have a space for an integer. And then you get a key with a room number. That room number is going to be the address, which is going to be these numbers here in hex. And the key is kind of like a virtual thing where like, it's like, think about like if we lived in the future where like we had like a RFID chip here, and all they did is that, like, they just assign it to you. So when you get to the room, it scans your RFID and it knows that you have the permission. And but it does have a permission system where like it says this memory is yours and nobody else can mess with it as long as it's yours. Okay? If somebody else wants it, they can't. It's reserved to you, and I, as the OS, I'm going to try to prevent other people. Now, it's not perfect for cybersecurity purposes. It's not perfect. It can't stop somebody trying to get in there. Just like a hotel really can't 100% stop somebody breaking in. Yeah, like they really want to, they can like, get a room near it and then like break the door in, or like, some Mission Impossible, go through the outside or something. They can still do that. This is not any cybersecurity thing. This is more like an honest man's thing, where like a drunk person doesn't accidentally stumble into the wrong room because they cannot just because it's unlocked, right? That's the people we're trying to stop. In this case, the drunk person is a bad coder who screws things up. Okay? But essentially, that's what the OS system's job is. And whenever you check into the hotel, you might check in tomorrow, you might get a completely different room. They have a system that you don't know how it works, you don't need to know how it works, to decide what room they give you. Same thing with the computer. The computer has a system to decide what piece of memory to give you, and that will change depending on the time you're running, what other programs are running, everything. That magic you will learn in 370, which is called operating systems. That's like lobby management or hotel management, basically, okay? But for now, we don't care about that. What we care about is just knowing that because those addresses are different, we can't rely on coding something based on an address because we know that it will change. So like anything else, we think of it as a variable that we're going to store somewhere. We're going to say, okay, whatever address we get is going to be referred to as A. So I can always say, int A gets 42, and I know that somewhere in memory, this 42 is being stored. And if I say A gets 41, that's all I need. Internally, the computer is going to translate that into whatever address it got this specific time it ran and go in there and update that number. Okay? But that is all happening behind the scenes. And that's how we've kept it so far. That's basically just bringing you up to date on what is happening up until today. Now, we're going to start to sort of ponder the question, what if, basically. Like, what if we start messing with these addresses? What if we want to, because right now, at compile time, you make all of these variables, like A, B, C, you make arrays, you make all these things. Don't think about vectors for now, that's special. But everything but vectors, you're making these specific variables. At compile time, when you turn in your assignment, you can look at your code, and I can see all these declarations of variables, and I can come back and tell you, you are declaring these many amounts of variables of these type. It's going to take this much memory probably, because it has like 5 integers. It's going to be 4 times 5. 2 doubles is going to be 2 times 8. So I go and say 20 plus 16, and then say, okay, you're going to take 36 bytes. This happens at compile time. Checks are done to make sure this is all good, of course. And when your program first is starting, so when you execute your program ./a.out and you run your program, that amount of space is declared. So that's like you checking into the hotel when you run your program. And the hotel will go ahead and assign to you. Usually it's pretty cool about keeping your party together per se, as a hotel would be, and they all assign nearby locations, but doesn't technically have to. Just like a real hotel that can be like, sorry, we're gonna have to put you on floors. So there's a lot of similarities actually to the hotel thing. I never thought about that example until today. I like that. But yeah, especially being Vegas and all. But yeah, so basically, you know that when the program starts and you get all of that space assigned to you. Even if you don't use it at the beginning, you still get it assigned. And when it comes time to use it, it's already there. You got your keys. You can walk in there, do whatever you want. And then when you're finished, when you check out, that's when your program terminates. You give that memory back. And then, just like a real hotel again, then the hotel can Well, actually, here's the difference. Whereas in a hotel, they will clean up the room for you before they give it to the next person. The OS is a little bit lazier about that. The OS doesn't do any cleaning. The OS is like, that's your responsibility. You know, the other client gives me the key back to this room, you get it. It's your job to clean it. And most of the time, it's not clean. So that is another thing that we're gonna have to consider. And actually, you already kind of saw that if you think about it. They tell you in 135, when you declare a variable, initialize it, right? Don't just like assume that like a 0 is there. If you want to use a counter and you want to start counting from 0, don't just like create variable int a. Like let's say we want to make a variable for count. We're going to call it C for count. You should not do something like this. And then just assume that it has a 0. And then like if I do C++ and I C out it, you know, I can't expect C to just have a 1 in it. Like that's a really bad assumption, right? What you do is you do that, or you do it in the declaration, right? That's called initializing your variables, and it's a really good thing because we don't guarantee, the OS does not guarantee that the variable is going to be initialized. And plus, like you might want to initialize it to something other than 0, right? So this is kind of the same concept. You go into the hotel, the first thing you're going to do when you go in that room is you're going to clean it up because you don't know what else is in there, okay? So I guess that is the variation from the hotel example. The hotel cleans it for you. Here, I guess you're going to like a 0-star hotel where you got to clean your rooms. Okay, so still all of this is happening at the beginning of your program. You're getting all of the rooms at the beginning. Now let's ponder the question. What if I had a lot of memory that I needed to use in my program? However, I only need to use it for a little piece of the program. The way you're doing it right now, you would have to book the hotel. Like it's like thinking of the hotel. Like let's say that you're staying 10 days in the hotel. But like one of the days you're gonna be hosting this huge party, so you wanna like get like the penthouse, okay? So like one day, but that's really expensive and it's a lot of space. So like you only wanna get it for that one day for the party. The 9 days you're not gonna use it. If you do it the way you've been doing it so far, when you need to use a lot of space, you have to declare it when you check in. So you're gonna be holding that space the entire 10 days. And in your case, the hotel is gonna cost you a lot of money. Would it be nice if during runtime, so like during your time at the hotel, you can go to the lobby and say, okay, I need to book another room, this penthouse, for this one day. So let me book it now. And they're gonna be like, sure, you can book it. You don't need to tell us how long, but just return it when you're done. You go, you use it for your party, and then the next day you return it. Okay? So you only pay for that time that you used it. Same thing here with the memory. If you're doing something really intensive, you probably don't want to allocate all that memory at the beginning. You know, you only want to use that memory when you need to, and then you got to return it afterwards so that you're a good program, so that you can cohabitate with the other thousands of programs running on your computer. And if you're doing something really intensive, you definitely don't want to hold that memory any longer than you have to. You can't do that with your knowledge so far. That's your limitation. You can run the same program, but you're going to have to hoard that memory the entire time. Dynamic memory allocation, as the name implies, is dynamic, allows you to be able to actually take that memory and reserve it at the time that you need it, and then use it, and then when you're finished with it, to give it back to the system, to free it, deallocate it. So we allocate the memory, use it, when we're finished with it, we deallocate it. And again, all that's doing is returning the key to the lobby so that they can give it to other programs. Again, you're not cleaning it, and you should also clean it before you use it. So clean before you use it, and then you don't really need to clean it when you're finished, because it's the assumption that the next person is going to clean it before they use it. Unless, of course, this is a security issue and you want to clean it. Want to remove the evidence of the party. Okay? So hopefully that gives you an idea to what we're going to learn. But before we can get fancy and start to allocate memory and whatnot, we need to learn how to play around with a pointer. So, what's a pointer? A pointer is going to be a type of variable. In fact, it's called a pointer variable. What it contains, we have integers that contain numbers, like integrals, or integer numbers, I guess. We have floats and doubles, which contain IEEE floating point notation values. We have strings that contain characters. We have characters, which are just numerical representations of the ASCII table. We have booleans, which are just 0 or 1 for true or false. And then we have a new data type, okay? So this is a new built-in data type to C++, which is known as a pointer. But a lot of languages have equivalents to pointers, or they have something, I guess, pointer light, which will be a reference, like Java or C#. C++ is like hardcore. It lets you handle all memory stuff yourself. You can get really, really down to like the low-level coding for the memory stuff. Other languages like C# and Java, Python, they don't let you get this low level. They let you handle some things, but the majority of the time they manage it, and that is for your protection per se. Because the more hardcore and low level you get, the more optimization and the more nitty-gritty stuff you can do. But the catch is, the easier things are to break, and there's no way I can emphasize that more than that. Okay? Yep, garbage collection. I didn't want to use that term because like I don't want to like freak you guys out with that. But yes, the C# and Java have garbage collection, which is basically like your you know, when you stop using memory, you don't need to worry about returning it to the lobby. The lobby is like monitoring you with secret cameras in the room, and when you leave the room, they know. So then they go clean it for you, and they go give it to somebody else. And it works great, but you know, unless you want to end up coming back to the room and finding a different person in there, you know, you have to be kind of have to be careful. Garbage collection has to be careful about that. So they usually kind of let things hang out for a while until they know for sure you left. And it works, but you know, it's not going to be as efficient. But the headaches you're going to save is totally worth it. So like, don't look down at garbage collection. It's amazing. Okay, it's a lot of talking, but very little actual coding. But I really kind of wanted to make sure that I introduce you to the why and kind of give you the overview. Because now as I show you these things, hopefully you can think back to that example that I gave you. Okay, so pointer variable. New variable data type that we're learning. The last one we're going to learn for the entire C++ time that you learn, because it's the only one that I don't really cover already. That is built in. At least see, you make your own, right? Not that you know classes, you can make your own data types, but like built-in stuff. This is the last one that's built in that you haven't seen so far, and those are pointers. So how do you declare a pointer? Well, pointers in C++. Unless you make a void pointer, which just forget I even said that word, you have to specify what it points to. Now, as the name indicates, pointers are going to point to things. So they're actually going to contain not numbers, not strings, not characters, not floats, but something called an address. Okay? So pointers hold addresses. That's all it is. A pointer is something to store an address. What kind of address do you think? The one I spent 10 minutes talking about. Hexadecimal addresses. Okay, sorry, I slapped the microphone twice. Hopefully I didn't just destroy somebody's hearing. Okay, so the way that I declare a pointer to hold an address is I put the data type that I want to hold. So I need to know if the pointer is going to be pointing to an integer, then I would like it to be an integer pointer. Why that matters is because, well, we'll see why. But I mean, there's reasons why. Okay? And then, of course, just like any other kind of variable, whether it's a string, float, double, or whatever, you need to have an identifier for it, right? So int A, int B, int potato, you also need to, you know, give it a name. So that's what your identifier is going to be. Now, you see this little asterisk in here, and you think, oh, wait, are we multiplying things? Well, no, it turns out that you've already seen how one character can be used in different operators in C++. If you think about the post-increment operators, you know, you have like A++ is basically A plus 1. You know, that plus is like the same one that you see with an addition, right? It's just a symbol, but it represents different things based on the context and where it's at. The same thing with the asterisk. The asterisk represents multiplication, and it's a binary operator in that sense when you are seeing it like with two integers next to each other or two doubles or whatever. But in this case, when you're seeing it in a declaration like this, or when you're seeing it as a unary operator in code, it actually is called the dereference operator. So let's write that down because it's an important sort of name. Oh, you know what? I have here, rather than writing that, last semester's class I wrote it. So maybe I save time by just copying and pasting definition. So I have two versions of this. I have paper notes but now I also have the notes from last semester. So, saves me time. So yeah, this asterisk is called the dereferencing operator, or also, I guess, indirect operator, okay? Although I typically refer to it as the dereferencing operator, okay? It's also the multiplication, but again, in this specific context, it's the dereferencing operator. So, what does it do? Well, as I say here, it refers to the object to which the operand, so the pointer, points. So, when you make a declaration, in fact, here I'm making a declaration, what I'm creating is, I am creating a pointer called PTR. Surprise, surprise, sounds for pointer, but you can call it whatever you want, okay? And just like any variable, it's uninitialized and contains garbage. However, and of course for any variable, that garbage is always going to be basically a bunch of zeros and ones, because that's all that computers can really store, right? But those zeros and ones are interpreted differently depending on the type of variable, right? If it's an ASCII variable, the zeros and ones are going to be represented as a number, which will be hopefully something in the ASCII table. Well, not hopefully, but it might be. In fact, you wouldn't want it to be, so you're getting weird data. But like an integer is going to represent as an integer, whether it's a signed integer or unsigned and whatnot, or long as well. So ultimately, in this case, those zeros and ones are going to be represented as a hexadecimal address. Okay? And that address could be somewhere in memory, who knows where. Like, it's just unknown. Now, sometimes, when you compile, if you don't initialize things, again, you get lucky and it gets set to 0. But you don't want to rely on that, okay? So how do you initialize a pointer variable? What do you even initialize it to? What does it mean to initialize something with an address? Well, really, you could initialize it to anything you want, right? Like, you could say that address 50 is going to be like my unknown address, but like it turns out that people came together and said, you know what? Let's just use 0 because we use that for numbers anyways. So you can initialize this to 0, and that's just going to be hex address 0. Although a lot of people say, it's an address, so putting a 0 there is kind of weird. And so they came up with, as you saw in the chat, null PTR. Well, they actually technically came up first with null with all uppercase, and then later on they transcended and said, hey, let's make more text to mean the same thing, and they came up with null PTR lowercase. So all three of these are going to basically do the same thing, which is to be used to initialize a pointer, or just simply set a pointer to a value that we have agreed and said, okay, we are never going to have this as an actual address in the system, but if we ever see a pointer set to this address, we know that that is just like an empty pointer. And so we can use it in an if statement. We can say like, if PTR is equal to null, then we know that this pointer is currently not pointing to anything of value, okay? And then we can say like, cout not pointing to anything. And why is it so important to initialize pointer variables? I mean, other variables is important to initialize. Well, okay, for all intents and purposes, yes. Technically speaking, null PTR is a C++11 thing, and I think it's implemented slightly different. So let's just say this: if you're gonna use null PTR, stick to null PTR. Don't be comparing like null PTR and null. However, null is literally a 0, so comparing 0 and null is perfectly okay. So really, if you're using C++11, stick to null PTR, but at least be consistent, okay? Because technically speaking, there is a difference between them. You might run into some issues if a class is created as null PTR and you're trying to use null with it. So yeah, but for like 99.9% of the cases, they are going to be the same. Okay? So yeah, stick to null PTR, but always stick to null PTR. Don't just throw in null randomly in there. Yep. So anyways, the point is that if I compare a pointer to null and I know that it is null, then that's sort of coder lingo for saying, okay, this pointer is not pointing to anything. Because guess what? If I try to access the address of the pointer, I'm trying to basically access a location in memory. if I try to access a location in memory that doesn't exist, or that I don't have permissions to access, the OS is going to be really mad at you. That's like, again, you're drunk, you're trying to go into a hotel room that does not belong to you. Or worse yet, you're trying to go to a room that doesn't even exist. So you like jump off a building or something by accident. Either way, the hotel's going to be really mad at you. So mad that they're going to kick you out. That's lingo for your program crashing and terminating. If you try to access memory you shouldn't access, most of the time you're going to get what is known as a segmentation fault, and your program will terminate at that point. That's, when you're playing a game and it crashes, most of the time it's because of a null pointer. You get that null pointer exception. That's where the name comes from, null pointer. So yes, that is also why people hate pointers, because when your program crashes, like, okay, if the lobby is cool, before they kick you out, they would be like, we try to kick you out because you try to access this specific room that does not belong to you. But that's usually not how it happens. How it happens is like, the moment you try to access it, you black out, and then next day you wake up and you're like outside of the hotel and you got kicked. And you have no information as to what happened. And if you have a lot of things in your code, then good luck trying to find out where that happened. Like, that's the problem with pointers. Crashes are hard to figure out where they happen. And that is why debuggers are like amazing, because debuggers is like, you put on a watch that tracks your location and you will see the last place you were before you got kicked out. And then you know that something happened there. And then you can go and investigate further and see, okay, why did it crash there? Okay? So, yeah. Okay. So going back to the basics of the pointer, let's just do some basic playing with pointers before we even talk about the allocation part. Okay? So let's go ahead and make a normal variable. Okay? When I do that, somewhere in memory, we don't really know where, doesn't really matter where, just somewhere, but for now I'm going to give it an address. We get allocated 42. So internally behind the scenes, at compile time, we know that we need this space. So when the program starts, you already have the space allocated, even if you don't use it in like the first line of code. So like if you have 100 lines up here, you still already have that sort of reserved. And it is when you get to that line that you actually use it. Okay? So let's make another variable. In this case, let's make a pointer variable. And we're playing it dangerously, so we're not going to initialize it, okay? But we should, but we won't. Okay? So, right now, this pointer variable has some garbage in it. So the question is, and by the way, when you do that, somewhere in memory, that pointer variable also exists. So somewhere in memory, we are going to have that pointer variable. And it has some garbage in it. Some garbage that is of a hex value. So like, let's just put a random hex value in there. Okay? How big, by the way? 32 bits or 4 bytes is going to be your app. Although, I guess if you're like in like a 64-bit computer, maybe your memory is like 8 bytes, maybe. I don't know. No, I don't remember how many. Maybe not. We can experiment on that next time by actually seeing how big the variable is. Yeah. But yeah, so that's important to also understand. The pointer itself requires space to store the address, just like any other kind of variable. And this pointer itself is not dynamic. It is also something that at compile time you need. So at compile time, you specify you're going to use a pointer variable. So when the program starts, the pointer itself needs a room too. So like the pointer itself has memory. We haven't done anything yet, but we still have 2 variables. They both contain 4 bytes of data. Right now, one of them has 42, the other one has garbage. So what if I want to store the address of my X variable? Okay, we're going to use a new operator for that. We're going to use an operator known as the address of operator. And then we put the name of the variable that we want the address of. So this will be read as P gets address of X. So the ampersand, let me try to write at least one nice one. There we go. Actually, do I have the definition here? Yes. Okay, let me just copy the definition over. Okay, So the address of operator, also known as the ampersand, that's the key. That's the one that's in the key 7 in your keyboard. If you hold shift, it's called the address of operator, and is basically a unary operator that is going to return to you the address of the operand. So just like the reference operator, they're unary. Unary means that they only have one operand. Just basic math to make sure we understand. When we say A plus B, this is known as the operator, and then A and B are known as operands. Okay? I gotta make sure we're all on the same page when I say these terms. So yeah, operand and operator. Okay. So when we say that this is unary, it means it's the other one's binary because there's left and right. Here, this unary because it's just one of them. So we have a unary operator has just one operand, and so we're saying that operand that you pass with the ampersand is going to be what you want to get the address of. Okay. So in here, when you see this line of code, P gets the address of X. We want to get the address of the variable X. X is the operand, the ampersand is the operator. So P gets address of X, okay? So what that is going to do is it's going to go and ask X, and hey, what room number is X located at? And, you know, dangerous, I guess, the hotel lobby person is going to tell them he's in room, or he or she is in room 55. Or in this case, he or she is in room 100. And so now, this will get replaced with that address. So technically, now you're pointing here. You are pointing somewhere. See, this pointer is pointing now because it has the address of something. So it's like holding an address saying that's where X is. So it's pointing there. Okay? So how can we see that? How can we see what the contents of the pointer has? Well, if I say cout P, that is going to print out the address. This is important. Make sure we don't get these flipped. This is going to print out the address because P again is just an address. So couting that address is just going to print out 0x100. And of course, if I run this again and this gets stored somewhere else, then it was going to print out that address. In fact, the one thing you can try, or we'll try probably next time, or maybe we have time today, is we write this code on the computer and we try to run it, and we'll see that every time we run it, we might get a different address each time. Okay? That is what's happening right now. P is holding the address of where X lives. Now, if that's all the pointers could do, there would be no fun. This is where things get interesting. You can also use the dereference operator, and instead of writing cout P, P, come back down, and 9. Instead of writing this, which we know just prints out that address 0x100, we throw in the dereference operator. We dereference address P. What that means to dereference address P is that instead of printing out the address, we print out what the address contains. And so now we say, okay, what does P have? Well, P has address 100. Okay, go to address 100, and print out what's in that address. So it's going to dereference it. It's going to go to address 100. It's going to see the 42, and it's going to print out 42. So the pointer is going to print out what it points to. Very important to understand the difference between this line of code and this line of code. P is an address. That's all it contains. Pointers, for all they are simply things that store hexadecimal addresses. Printing them out like this will just give you the address. No fun there, especially because it's probably random. What is fun is to say, okay, cool. What's in that address? Okay, I can tell you. Just dereference it. Put an asterisk in front. Now we're in business. We get an address out of that. We go to that address. We get the value of what that address contains. That's the power of pointers. So now, let's do more cool things. Okay, so we know that prints out what the 42 is, but let's go even further. let's put the P. Well, okay, first of all, if I have a P like this, and I just go ahead and put in number, 555, what's that going to do? Well, first of all, this probably won't compile because C++ does not like you hard coding addresses like this. But assuming that you got it to compile by turning on F permissive, which here I'll write it just so you're aware. You would probably never need to turn this on unless you're doing really bad things. But you never know. Great power comes with responsibility. Go have fun. But if you do something like this, because P is a pointer variable, what this line is being interpreted by the compiler as is you trying to hard code the address 555, whatever that is in hex, from decimal to hex, in there. So like this would literally take, here, let's do our Google. Oh, now I just minimized everything. Hold on. There we go. Okay. So if we go in here and say 555, convert to decimal, convert to hex. Where's hex? Oh, decimal to hex. 22B, 22B. So it's going to go into memory, and it's just literally going to store a basically 22B. So up here, instead of 100, that would store 22B, which of course is pointing to somewhere in memory, like down here, 22B, which is just like who knows what. Because it's not ours, it's some neighbor's program. If we try to access that, we're probably going to get kicked out, crash. But, just thought I'd show you that, okay? However, again, because you don't want to do weird things like this, like hard coding an address, because it's never a good thing. The compiler doesn't usually let you do that, and if you do it, it'll give you an error unless you do a flag, which is like the YOLO flag, which not good. Okay. So, anyways, that's not the point. The point is that what I want to do is I want to add one more thing to this line to actually make it an interesting thing. That this has a whole completely different meaning now. I am storing 555, and this time it's a decimal value, but I'm not storing it in the pointer itself. What I'm doing is, again, I'm dereferencing the pointer. So what I'm saying in this line of code is dereference pointer P. So get what it contains, which it currently contains address 100. Or again, I keep saying 100, but it's in hex. It's not the same, right? And store value 555 there. Okay? So what I'm doing is I'm taking this 42 and I'm actually replacing it with 555. So yes, I have replaced the value of x indirectly because I never have any mention of x in this line of code, and yet I've replaced somebody else's x. So this is like saying, well, they all belong to me because that's why I'm able to access them. But this is me saying, hey, this key card says it's an address to another key card, which can then open the room. And I'm using that to indirectly access the room and edit it. So pointer variables are not just limited to access. You can also edit, delete, do whatever you want with them. Okay? They're powerful, but they're also risky because of that. Because you are adding a level of indirection which can be misleading to somebody, because somebody might be expecting, somebody's looking at your code really fast and they're like, okay, there's an X with a 42 in it. They might look at this line and not realize that this is actually modifying the X, because there's no X in there. I mean, unless they actually catch this line that is telling it, it's like, oh, okay, we're actually making a pointer point to X. Nobody knows that this actually modifies X. And so they might miss that, and they might be like so confused, like, oh my God, why isn't the code randomly like X going to like 555? Like, I don't understand what is happening. And until they go in the debugger and manually see what is going on, they see, oh my gosh, this line of code is actually modifying X indirectly. Okay? So that's the power of pointers. This is one usage of them, but not the main usage, which is of course dynamic in-memory allocation, which is what I'm getting to. But we have to make sure that we are on the same page when it comes to pointers. Oh, I minimized the chat when everything got minimized. So let me actually open that up. Oh, okay, nobody said anything. Sad. Okay. So, yep, that's one page done. Okay. So again, right now, all we're doing is creating pointers and making them point to other things. You can, of course, make this point something else. So like, for example, if I said int A and int B, and then I make a pointer. Again, the pointer has to be the same type of what you want it to point to. There is a thing known as a void pointer, which kind of gets around that, but no, don't do that stuff. Let's initialize our pointer because we are good coders. And then, visual representation of what that looks like. Let's say that that's where A happens to be. So I'll just put a label as A. Somewhere else in main memory here is B. And then somewhere in here is PTR. Again, these are arbitrary values that I'm just throwing in. Okay? So if I say PTR gets the address of A, what this is doing is just copying whatever A is. So that would be 400. I can then go ahead and assign value to that by saying dereferencing PTR 10. So what that's going to do is that's actually going to assign the value of 10 to A because I'm dereferencing what the pointer contains. So I'm saying go to address of the pointer. So go to address 400 and then assign 10 to that. So that's the address of A. I can then, of course, update the pointer again and say PTR gets address of B. And so now PTR is going to get address, I believe we said 550 here. Let me make that easier to read. Oh, close enough. 550. So now I can do the same line of code. Let's just change the number though. Let's make it a 7. So what that's going to do is it's going to dereference address of PTR. So it's going to go to address 550 and then it's going to store a 7 there. And see, nowhere near did I actually modify A or B directly. I'm using indirection. That's why dereference pointer is also known as the indirect operator. Okay? Yeah, I think we can move on from that. We'll see more examples when we code. Okay, before I show you dynamic allocation, I would like to show you how to use pointers for classes. Since we learn classes, might as well learn more about pointers now. So let's go ahead and make a little class. We're gonna say class, what was the rocket thing that we did? We did like class rocket. And then class rocket, we had the thrust to weight ratio, right? So we had, I believe that's a double. Well, I don't know if we did it into a double, but I guess it makes sense to make it a double because it's decimal value. So let's say double thrust to weight ratio, okay? Just to make our life easy, let's make it public. All right, so if we have on main an object of the rocket, so like we had the Falcon 9 rocket or something, we can say something like rocket. And by the way, good practice to do when you're naming things is you can say rocket T. That means rocket type. It's just a naming convention some people like. So I have it on a different example, so I thought I'd bring it up. But yeah, let's say we're making Falcon 9, so F9, just because I don't want to type a lot or write a lot. And then let's say that we want to make a pointer to that. So in this case, because we're going to make a pointer that points to rockets, it has to be a rocket pointer. So we say rocket as the data type, put the dereference operator, and then we put the pointer. So I'm going to call it RPTR for rocket pointer. Okay, so again, what this line of code is, it's a pointer variable of type rocket type. Okay. Next, again, just like I did before, if I would like this rocket pointer to point to my Falcon 9 rocket, then all I have to do is assign it the address of the other object. So in this case, I use the ampersand. Let me make it nicer. I'm struggling today with these ampersands. All right, there we go. And then F9 for Falcon 9. Okay. So what I'm doing again is I'm storing address of Falcon 9 object in RPTR. Okay? Storing address of F9 object in RPTR. So how does that affect our member access operator? Remember, the dot is the member access operator, right? Well, let's see that. Okay? So, to access, if we want to access like directly, if we were just dealing with a non-pointer object and we want to access that trust to weight ratio, we know that we use the member access operator dot, and then we just say f9.twr, or if it's a function, the same thing, and then we can say assign that to 1.5 or whatever the trust to weight ratio is of the Falcon 9 rocket. Okay, we can do that. Cool. However, if you try to do that with the pointer variable, so remember we have our pointer called RPTR dot twr, and if you try to change this to 1.51 or something, if you try to do it like this, you are going to find yourself looking at either an error or it'll crash again, because probably it'll crash. Actually, no, it'll give you a compilation error. Here's the issue. First of all, what do I need here? Well, remember, if you're trying to modify something in the object, you need the dereference operator. So first of all, I need this. That is like a starter. So now at least maybe it'll compile. It'll probably crash when you run it, but at least maybe it'll compile. Maybe still not. Why do you need the asterisk there? Because remember, the RPTR is just an address. If you're trying to access what the address contains, you need the dereference operator. So again, like we look at the example above it, when I'm trying to access a number, when I'm trying to access whatever PTR is pointing to here, I need to dereference that. So this says, okay, get the address of PTR and go there. So what does PTR have? Address 0x550. Okay, cool. Address 0x550, go there with the asterisk, go there, and then actually assign 10 to that address. So similarly, hopefully that makes sense as to why we need the asterisk here. I'm saying this address here, go there. So in main memory, somewhere in here, address, let's just say 90, there's my Falcon 9 rocket. So F9. Somewhere else, very tiny, I have my address for the pointer for the rocket. By the way, that's an interesting thing. The objects might be really big because you have a lot of variables, but the pointer is always going to be the same size because it just stores an address, and all the addresses are the same. Just because an address is smaller, like if you have a hotel with like 1,000 rooms, if you're storing room 1, versus room 1,000, you just make it so it fits 4 digits always. So both like, let's say both key cards are going to contain enough space to store either a single-digit room number or a 4-digit room number. Same thing here, because of the way addresses work. You don't save space by storing an address closer to 1. They all take the same space, okay? Except you just fill it with zeros. But anyways, so you have your RPTR, and since we assigned that to point to Falcon 9, then this becomes 0x900. And in this Falcon 9, it turns out that when you have an object the address of the object is just the address to the first parameter or variable of that object. So in this case, our object only has one variable. In fact, let's just throw a second one in just to have a second one. And let's call it version. What that means is that, like, internally here, it's going to have the TWR right here, and then beneath that, it's probably going to have the version and so on. But this points to the top of that object usually. Okay, we'll play more around that when we get done later. Yes, I'm going to get there. I'm going to get there, but I'm not there yet, though. I'm glad that you know that that's how you do that, though. But yes, so right now, you can see that you need to put the dereference operator because you need to be able to dereference it. However, as I said, this is not enough. This may compile, maybe, probably not, but it will definitely crash at runtime. Here's the reason why. You have the right concept in putting a dereference operator here because that's going to get you to the address of 90. And then once you're there, you of course want to dereference that address location for TWR, which is going to be some sort of offset, which in this case is just 0. However, while the concept is right, it turns out that you run into a problem with order of precedence. You have two operators here technically. You have a unary operator and you have a binary operator. The unary operator here is the address of operator. The binary operator is that member access operator, the dot. Okay? So this is an operator and this is an operator. This operator has a right to it and a left. The right side of the binary of the address of operator is going to be the field that you're trying to access. The left side is the object reference you're trying to get to. The address of operator has a unary operator, which is after, which is just whatever you're trying to dereference, and it should be a pointer variable, which it is. The issue here is that these two variables have precedence because here's two ways to interpret this line. Okay? This line, you know, the asterisk, the reference operator wants one thing because it's unary, right? So it could either, in fact, here, let me write this a couple of times. 4 scenarios. 1 correct, 3 are bad, I guess. Okay, so one scenario is for the unary to interpret this entire thing as its unary. Okay. Another way is for it to interpret just this piece as its unary. On the hand of the binary, so on the hand of the dot, it wants two things. So it can take this and this, or it could take this and this, right? So if you don't have any parentheses, any of these could technically be fair game. However, just like in math, there's order of precedence, right? They make a decision and say, okay, multiplication has priority over addition. That way we don't have to put a billion different parentheses whenever we have a long operation. And so the closest equivalent to this in math would be like saying, let's just say the asterisk is some value times RPTR, which is some value, plus, or actually, no, my bad, other way around. This will be like plus times TWR, okay? So this is what it would really look like in math. So you can see here that in math, the multiplication will happen first, right? So this will happen first, and then this will happen second. That's not what we want. Because we need to dereference RPTR, we need to go to that address. And then once we're at that address, then we want to access the field trust to weight ratio. Currently how it is, it's actually doing, of the ones that I drew here, it's technically doing this first. And then from there, it's doing this. Okay, so 1, 2. That's what it's doing. What we want it to do is, I actually don't even have technically that that I have that. We wanted to do this. We wanted to do this first as 1, and then this as 2. Okay? So, in other words, we want the addition to happen before the multiplication. So what do we do in math? We just throw in the parentheses. So we say asterisk plus RPTR times, I'm using a lot for times because it's like a lot in the code, thrust to weight ratio. Okay? That is why, and that's why somebody in the comments said about the parentheses. Okay? But I just don't want to throw you the parentheses because then you're just like, why? Or, you don't get it. But now you understand why. Now you actually understand, so you don't make the mistake and you actually know when to add them or not. The order of precedence has higher precedence as the member access operator over the dereference operator. So member access operator has higher precedence than dereference operator. Okay? Because of that, and we want to dereference before we do member access, we are forced to put the parentheses. So yes, the final version of this goes from being asterisk RPTR dot TWR equal to 1.51. We have to add these to ensure that the dereferencing happens first and then the offset of thrust to weight ratio happens second. Okay? It's a very, very fundamental thing that you have to understand about this. Otherwise, you won't get it when it gets more complicated than this. Let's go more complicated than this. Let's say we have class A, and class A has an int x in it, okay? Let's say we have a struct B. Struct B has a int y, but also has a class A in it. Okay? And finally, we have a class C that has int G, and it has an object of B. Okay? So, in main, I make an object of A, I make an object of B, and I make an object of C. And yes, they're all objects, even the one says struct. Remember, that's just a thing from C. Okay? So, suppose that I would like to access in my object A the variable x. No problem. A.x. Done. Suppose that I wanted to access the variable x found inside of class B or struct B. So if I want to access, actually lowercase a, not uppercase a, my bad. If I want to access the B inside of A, or sorry, the A inside of B, or yeah, the A inside of B, then you do B.A.x, right? That's that composition we talked about last week. Of course, if you want to access the y, it's just b.y. Now for C, if I want to access the g, it's just cg. But now if I want to access what is in B of C, we go c.b, and let's say we access the y, we can do c.b.y. If we want to access the x inside of A, inside of B, inside of C, then that becomes C dot B dot A dot X. Okay? Yes. Still, not too bad if you look at the dots. It's just nice and clean dots. Like, nice. Wait till you see the version with the parentheses and the asterisk in a minute here. It's going to become kind of scary. Okay, so now let me take this entire piece of code and shrink it because we're going to want to reference it. So yes, this is going to be pretty scary stuff. Don't worry, I don't think you'll ever have to do something like this. Although I did make it an extra credit once in the test, but that's when I used to make tests. I don't make tests anymore, so I don't think there's any extra credit in the test now. Sad emoji. Okay, so let's try to do this with pointers. Let's just kind of go from A, B, and C. Okay, so let's make pointer. So we'll call this APTR. So that's an A pointer. So oh gosh, I want to introduce other stuff, and we're going to talk about it like 2 weeks ahead of time here with like virtuals and whatnot. But yeah, so A asterisk APTR get address of A. So that's going to basically make an A pointer that points to A. That's what I've been showing you just a minute ago with the rockets. And we'll do the same thing for B and C. We'll call them BPTRs. Oh, this one should be C. And this one's going to get the address of B and address of C, okay? So like, just imagine, in fact, I'm going to shrink that, but just imagine that that code is right beneath this code, okay? Or somewhere in there. Okay, so we got 3 pointers, okay? Now let's try accessing the easy variables first. So let's just go for each one. So for A, so let's color code what line we're gonna do. So let's try to, in fact, let's just do them side by side. Yeah. Well, we'll try. We'll probably have to shrink them as we put them in. So let's start with AX. How do we do that with the pointer system? We do APTR. Here, let me do it bigger. APTR dot X, but of course we gotta dereference it, and then we gotta add in the parentheses, right? Okay, that's what we just saw like 5 seconds ago. No problem. Okay, we just handle that one. Let's shrink it so that it fits in here. In fact, I think we can. You got a little extra space. Let me do something here. We can make this a little bigger, like that. Okay. Yeah. There we go. Okay. So this would be the equivalent line to that. Okay. But using the pointer. Let's do the other easy ones first. So like B.Y. That one is just going to be BPTR, because again, that's what we call the pointers up there. So BPTR dot Y, and we put the parentheses there. Same with the CG. That's just going to be CPTR dot G. So those are the easy ones, no problem. The nasty ones are the ones with the 2 and 3 dots. So let's do the BAXY. Okay? So just for now, move this down for a minute, and let's try to do this one. So BPTR, I'm just going to write it down first without any parentheses or anything. Dot, and of course, don't forget the asterisk at the front. And then A, which is just an A. And then X. Okay? So, actually, this is not too bad. This one you just put like this, and you're good to go. Yeah, not as interesting as I thought. I had to modify the example to show you what I really wanted to show you. But okay, this one should be good to go then. Okay, and then let's do the other 2. So actually, I'm gonna do them fast because this is not what I was what I had in mind. So I'll just do this quickly. So this will become B, and then this will become Y, and then I assume that you can see that this one will be CPTR dot B dot A dot X. Okay, but that's not what I was trying to do. I gotta tweak my example slightly to show you what I really wanted to show you. Suppose that in class B, you know, I'm going to add an extra variable in here. I'm going to add a B pointer called B point, and I'm going to assign that to the address of the other B, okay? So I'm making this point to this. All right? And I'm going to do the same thing with A as well. So I'm going to add in here A asterisk A point get address of A. That's what I wanted to do originally, okay? So now that that's set up, let's go back to those two lines. So we had BA.x and CBA.x, okay? So now let's do those. And feel free in chat to try to do the last one. Well, I'll do the second one. Okay, so again, we start with the BPTR as we've done before. BPTR. Oh, actually, instead of A here, though, we want to use the pointer, of course. So like, what this will look like is BPTR.aPoint.x, right? However, this aPoint is also a pointer. So this is good to go. However, we need to add an asterisk to the aPoint one. So like, we could try doing this, but like, that's not really gonna work because like, it's gonna get super confused and be like, huh? So it turns out that this asterisk, because we actually need to combine the address of this with this before we can get that. So what we gotta do is we gotta move this asterisk to the end here, like that. But then we have the same issue with the order of operations that this is happening before the dereferencing of this. So we need to put a parenthesis here to here so that the order this happens in is first we were going to do this, and then we're going to do this part here, and finally we can go ahead and do the .x part. As you can see, that's kind of nasty. And finally, for the CBAX one, that one would be CPTR dot bPoint dot aPoint dot x. We need asterisk for the other two, so then this has to be done first, then this has to be done second, and then this has to be done third. So yeah, can you do that on the test if I put you on the spot with all the parentheses and make sure you don't screw that up? Well, you know, if you do it a couple of times, it's actually pretty easy. But definitely when you first see it the first time, you're like, oh gosh, this is nasty. This sucks. So right now I know you're thinking, oh my God, I'm never going to use pointers for classes. Like, that's just horrifying with the parentheses. It's parentheses mayhem and asterisk mayhem. It's like, no. Well, there is hope. And the hope comes in the form of an arrow, aka the arrow operator. However, it will have to be a cliffhanger on how that will come to save the day because we're out of time. So on Wednesday, tune in to see how operator will save the day from you having to put this type of code in the test and having a nice and clean solution for that. Okay? So, yep, that's where I'll end it. But yes, the arrow will come to the rescue on Wednesday. So yeah, today you got to see some basic pointers, understand the idea of pointers. Next time we'll do the arrow operator, and then we will do dynamic memory allocation. And then that'll be the end of the week. So the arrow is indeed going to save your lives, and it'll be MVP when dealing with pointers in classes, because they will make you sane, as you can see from that. But yeah, we'll see on Wednesday. Of course, you can spoil it by just Googling it if you want. But if not, then on Wednesday you will know how to use it. And it'll look really nice. So, yep, that's the class. Thank you all for coming. And I'll see you guys on Wednesday. Have a good week, everybody. See you later. Thanks all for coming. Bye.